So today we will talk about human-centric explainable AI approach in healthcare, but I will tell you a little bit before about me and why we need a human-centric AI. So, but I'm sure, now you know more than me that all these models that we've been seeing, all these days, all these models, we ask them to predict, and predict. So they are predictive models, but they are black boxes. So I don't know if you've heard this word before. We will go through it, hopefully, and I will try to connect and approach this from different angles, from the ethics angles tomorrow and from the creativity entrepreneurship the day after. So, but the question becomes like, is it easy to break into black boxes? Because we really need, to understand, like, how do they function? How do they predict, and how do they make decisions, So coming to this, I care very much, in my lab about how to communicate this to the public, how to communicate this to non-experts, how to communicate this to policymakers, because we really need to connect all these dots together. So I have a great artist, working for me, and in this allegorical representation of a human to the left and the alter ego, the AI, which is a perfect deputy, if you want to call it, a partner. We will see, if we want this. And it's a nice representation of these green and turtle like branches of the plants, that it's a feedback loop, that we can learn from each other. And they interact with each other because we want them really to help us mitigate bias, perform better, and give us some like ethical and responsible, output. So we use this hopefully to be more effective in science communication. So we will be talking about what's this about human-centric AI, because we proposed this to the editor of Trends in Plant Science. It's the best journal in our area, and it's been very tough, to go through. But this is already there, and it was featured on the cover. So please, if you want more details, if you want to learn more, go to those papers, that I will be showing you. So now, of course, all of these things, AI, the one what we've been hearing, because we want AI application, we want to use AI in different applications. We've been hearing about it. And if we connect it just to the previous talk, about SDGs, we have SDGs spreading over everything, and we cannot have good health if we have food insecurity, for example. So in my lab, we work a lot on plant science. We want to accelerate breeding, and we want to improve, like food security, nutritional security as well. We want plants, future-proof plants, that they can resist climate change and so on and so forth. So one of the words that I would like to highlight here, phenomics, this word has been borrowed by human phenomics, medicine phenomics. We will be seeing it later on with the exercise that we will be doing together. It's the same thing, it's more complicated in plants. I study the plant immune system, and I want to know how it works, So, but here, just to show you a little bit about me, just imagine here you are in a hospital, a patient in a hospital, and he has to be screened by so many platforms, so many sensors, that means that we get a lot of data, So the way we do it, we get data from satellite, data from drones, unmanned aerial vehicles, data from sensors on the ground, data from growth chambers. And this is the same way hospitals also work, that we will see in our example later on. Of course, these data are very challenging, highly dimensional, highly complex, and we have this so-called big data, and we want to understand, are we getting everything we want from this big data? Are we making sense of this big data? So the question becomes very tough. Here, just to give you really an example of what's going on in the real world application. So you can see those, we borrow those sensors, from human medicines. We mounted them on drones. Drones hover over the trees. Trees are challenged with drought stress, for example, and we want to understand, everything, the genes behind, at single cell level, at tissue level, at organelle levels, and we want to phenotype them, how throughput, and we want to genotype them, and then we get into too many data again. Please visit also this paper if you want to deep dive into what I will be showing you quickly here. So we want to bridge, different omics together, and we know very well that statistical models, they really fail to explore nonlinear relationships, so we want artificial intelligence. God, thanks to Turing and whatever, even with the winter period that we have experienced, let's learn from them what we have seen the first day from the incredible speaker from the University of Columbia, so he's challenging us also again, we need to be less artificial, or we need to be human-centric, or we need to be whatever we want to be, okay? So to do this, we have really to care about the experimental design. We need to care about the data, and we know we need not to miss, not to forget, the G by E, genotype by environment is the phenotype, whatever we are getting, The interaction with the environment is so important, and any change, in this, it will affect, it have major impact, at different levels. So in this paper also for you, if you want to know more, it was the first paper to set the stage about the 8 V, we call it the 8 V's, the 8 attributes of big data, the data that we collect in human medicine or in plant medicine. So I'll go just quickly through them. Volume, we mean by volume the size of the data, the value is the data knowledge, and we will get into this when we are into the ethics tomorrow with the ethics decision-making model. Velocity is the data speed, variety is the data types, variability is the scale of the data. Visibility, are our data readable, accessible, they are fair, do they follow also the FAIR principles? The data quality is very important. Is it trustworthy data? So all this question becomes very important if we want to get from AI a responsible, decision. So then vaccine, how's the model? Is it effective? How does it function? How does it work? So to do this, we need really to think about, so in this paper, we called it next generation artificial intelligence, because our editor, he said, I saw it first, I want to call it AI 2.0. And he said, no, it's too much, because maybe it will become, somebody will say it's 3.0, but this is setting the future, because we will see, so let's call it next generation AI. So with AI, we can do predictive analytics, we can do prescriptive analytics. And this process that goes from input to output to get intelligent features, and insight, we want to get, to highlight the genes, alleles, gene networks, as we have seen also, and we've heard the first day from another professor, the Greek professor, I think he was from BRFA, the IOS, something like that. So he was talking a lot about these things as well in human medicine. So this is what we need to do. We need to design, we call it something called idiotypes, plants, ecotype, genotypes that they can prosper in specific niche environment. And we will tell you how we are doing this. So, as we said, one omics data will get one result at a time. But we are not getting really to the real, we are not getting the full picture, and to get the full picture, thanks God that, the sequencing, cost is plummeting, continues to plummet, and now it's becoming routine, let's do epigenomics, let's do transcriptomics, look at RNA, let's look at protein, let's look at the metabolite, let's look at the phenotype, let's look at the microbiome. And in this paper, also, it's a very good paper also, let's look also at the environment, all this environmental and climatic data that they are impacting, on the interaction with the genotype. So this means that our data goes from matrices, 1D to 2D matrix, cubes, two-dimensional, then to polytopes, because this is what we need, and this is the big challenge here, how we are going to deal with with arbitrary dimension and generalized data space, we call it the polytopes. So in this paper, if you go and look, you are now familiar with the neural network, so we know that if we want to use neural network, we can feed different omics data into different nodes of the layers, of the architecture of the neural network, or we can also use the decision tree, because they are actually, they can give us interpretable structure. But again, if we want to use random forest is not the case. So in this paper, with my colleagues in the United States at Oak Ridge National Lab, they developed also, and Berkeley National Lab, they developed the IRF, which is the iterative random forest. But again, iterative random forest deals with one omics data at a time, and then now they are developing, the tensor iterative random forest that can deal with with arbitrary dimensional spaces. So, just connecting to this beautiful talk before lunch, we come up to, with another paper. Please visit also this paper published in Current Opinion in Biotechnology. It's about like, okay, we have AI, we have good architectural design, of an algorithm. We know about how AI is going to help, in respect to statistical modeling. But do we really need only AI, or we need also something else with AI? So we realized that we really need exascale computing, because when my student were piloting, the drones, just a flight of a drone of 5 minutes, they get on the floor and we have like 100 gigabytes of data. So do we have the right computers? Do we have the right systems, and so on and so forth. So I don't know if some of you have seen supercomputer or heard about supercomputer. If you don't worry, because we don't have so many here in Europe. The leaders are the American and the Chinese, but Oak Ridge National Lab is where my friends work, and I visit with them so often. They house the two big fastest supercomputer in the world. One is called Summit, and the Frontier is the new one. But we have created for you in virtual reality, a supercomputer, a data center, and we will be visiting it the day or tomorrow or the day after. So I will be asking you a little bit, of patience, at the end of my class, how to set you up, to get into the virtual reality and visit, data center and interact with it in fully immersive to understand what is it about. And Farid is going to help us with this. So we get to realize that we need to fuse exascale computing, and I will tell you what we mean by it, and explainable artificial intelligence. So exascale computing means that we need to make so many calculations, at a time. So exascale, it's 1 quintillion, it's like 1 billion, calculation per second. And if we can do this, we can handle all these data and we can get into all these intelligent features, that I showed you. So in this paper, the good things about it, what we've heard also before, what we were able to do, we did clusterize the planet climatypes. Okay, so if we went to get the data for the climate for the last 50 years, planet climatypes, and we clusterize them. And as you can see here, different colors, this means that what's the climate and the environmental factors that they are of the, of the genotypes, the location, specific location at 1 square kilometer, resolution of how we can do, how these genotypes evolve, and survive there. And if we can do this, we can design multi-criteria, idiotypes, and ecotypes that can survive in any climates. So by doing this, the paper was focusing on, are we really achieving, are we close enough to sustainable development goals? So please go read the paper and you will see that we are. So it's enough about me now. Let's talk about, you've been working much on machine learning. I don't know if you questions, your lecturers, they are all incredible. How does this connect AI? When we hear AI, we hear machine learning, we hear deep learning. What's the connection between them? So in one of the paper that you will have also as well, the human-centric one, sets the stage also, like according to us, we believe that AI is a science. It is a technology, but it is a science for us. We are scientists, okay? So it's the science that needs to deal, like to study, to design, and to develop intelligent computer systems that can perform tasks that normally require human intelligence, okay? And of course, we know every day, and I will show you because you will see at the end of this lecture and the exercise that we will do together, a palpable, question that is being asked, and AI is stepping in to answer. So machine learning becomes a particular approach to AI in which intelligent systems learn and derive models from training data sets. This is what you've been doing with the machine learner, and then you did, I think yesterday also with the deep learning, which is specialized brand healthy cassava, okay? So we ask question, what's the phenomics questions to be answered? What are the target classes or variables? Is the target mutually exclusive, class? When we do plan, after problem formulation, we go into data preparation, okay? So questions, don't get afraid. It's not big list, it's easy, sometimes very, and if you do so at the very beginning, you will find out that your results are so much nicer and accurate and verifiable and whatever you want to ask. So our image is taken in a controlled environment or in the field because we will need to take care about the G by E. And this is the same thing like, let's say in human, if we have research participants and maybe they have other diseases, you know, so, okay, so there are so many variables that we need to take care of. We have sufficient data. We have enough features to distinguish between, you've seen features, you know, the first day when we've been together. Are the labels accurate? Okay, if we don't have good annotation, we are not going to get good results, okay? Is the data balanced? Are we missing some values? Okay, do we need some pre-processing task? Do we need to clean? Okay, do we need to split, whatever, okay? So we'll do all of these things, but you will do this, you will follow these things, and you will do it with Farid, you know, after break. So we split the data. Again, here we have so many ways to do it. You have seen the first day when I was with you, you take 80%, 10%, 10% for training, validation, testing, or 75, 15, it depends, you know. We will see. I mean, these things should be decided, you know, with a team of people. We'll see if we need to crop, you know, like these images or not, because we can get better patterns, features, you know, from the algorithm. Then we train the data sets, you know, and if we need to oversample, you know, we can think about all the ways that I've showed you, you know. If the data are imbalanced, if we have some biases and so on and so forth, we can deal with it. And if you remember the technology infrastructure, you know, and it's very important because here I show you the same examples that we've done in this paper. If we use our desktop server, just normally we have CPUs, computers, some of them 1 or 2 GPUs. This can get so many days. I don't see it clearly here. It's about how many days for it? If we want to do this on GPU computer, we shorten the time. If we want to do it on Colab, for example, and this is the exercise that we'll be doing together, it's also different. And if we want to do it on exascale supercomputing, we get down to hours, okay? From days, almost years, to hours, okay? So here, where it comes, you know, why it's important, the infrastructure. So, I don't know, I am running out of time, but here, what I can tell you, I'll go through this quickly. So we did it, as I told you, we have 2 dichotomies of explainable AI. We can either open the black box by post hoc or model agnostic, or we can do it by interpret or by design. So this is another paper. I invite you really to read this paper. It's a very nice paper also, and there is a free tutorial. You can really get your hands on, you know, and learn a lot on things like this. So we have here tomato. We have 10 different diseases, fungal diseases, obesity, viral diseases, you know. Again, here what we've done, we compared random forest and a pre-trained DenseNet, which is a neural network, and then we got into explaining this data by opening the black box using Lime. And Lime works in 2 different ways. So quickly, philosophically speaking here, what it does, you can see here the leaf. This is the original image. And it does like superpixel segmentation, and it tricks, you know, the algorithm, and you have to monitor, you know, if I take out some of the superpixels, you know, is the algorithm classifying this as the diseased or not diseased, or which disease, and so on and so forth. So here we have just a few examples, but there are hundreds of these tricks here. But you can see here the green area, which represents the location that has a positive effect on classification. Here, we are not satisfied because I wanted all the time, you know, in my lab to ask so many questions and do it so many different ways because I want to understand which better results is. So usually this is based on, we call it quick shift superpixel segmentation, and I wanted to use also the compact watershed. As you can see here, the pixels are smaller, and we are narrowing down, and if you can see, it's always the same area, but here we were losing some information, okay? So the green area always represents the location that has positive effect. Again, we have explainability, but we didn't know, actually, we don't know yet, how does the model function, okay? So we should think about inherent explainability, you know? So we did this in plants. I don't want to anticipate how does this work. We will do it in humans. This is your exercise. Again, this we leverage an algorithm developed by Shinsirudin at Duke University, very nice. We used it in plants. It works very nicely. We did some tweaks here and there. And again, you know, cassava, 5 different classes. This is the architecture that Farid will go into it. So we first train and we ask all these questions that we have seen before. And what it does this neatly, actually, while training, you know, it generates prototypes, you know. So the other one is by approximation, and we don't know the inner working, you know, how the algorithm is approximating. Here, what you can see, so after training the algorithm, and we have the good models, you know, trained to classify diseases, we give it a new image, test image that haven't seen before. Okay, and then it classified as brown streak. Why, Mr. Algorithm, you classify it as brown streak? So it generates those prototypes, as you can see, these bounding boxes. Here from the heat maps, you know, this is the area where the algorithm is focusing, you know, and is trying to understand, you know, that this disease is brown streak because of these features within these bounding boxes. Usually we do a confusion matrix also to see like binary and multi-binary comparisons. So it's very important. You can see here high percentage, you know, of accuracy, you know, of this. We will go into details. I don't want to lose your time because I have more slides to show you before we dive deep into this exercise. Do the same thing into breast cancer, and I will show you the data. So here, the question is, we are trying to call it, this is a paper under preparation, so we are still working on it. What we need to embed into this paper, human in the loop, that I will tell you about it in a bit. Interpretable by design model to classify benign and malign subtypes of breast cancer. Unfortunately, as you know very well, we would love to work on many different data sets. It's not easy to get access to data sets, you know, but we will show you, you know, a couple of. This data sets is very good data sets, you know, it's called Brecis. Comes from Brazil. It's highly cited in Google Scholar and in Scopus, the University of Federal University of Ghana. And it's very good data sets that allows us to design and do an explainable human-centric AI. So we have 82 patients, you know, surgical biopsy. They got tissues, microscopic examination. They diagnose and label, you know, it's labeled by pathologists, you know, and then to validate, they do immunohistochemistry, okay? So very good data sets. But as you can see here, what you can see here, go ahead, quickly. Unbalanced data sets, it's problematic. Please don't give your algorithm this data. The algorithm will give you output, okay? It will be overfit maybe, okay? So we need to think about this. Of course, you know, on the ethics, please also think about those words now. Data sets anonymized, you know. We need to obey, you know, to the rules, GDPR, personal data, all of these things. Hopefully, when on the bioethics decision-making model, we should also take care of this. So Farid and I, we decided to train 80%, you know, and then validate and test, and then do the geometric transformation to oversample. So we got 4,343 and 4,000, okay? Now we have it more balanced. This, Farid will go through this. Farid, you hear me?
Yes, I'm here.
Yeah, go on, explain the architecture quickly.
Okay, so on the slides, you can see this is the architecture of a convolutional neural network. It's a black box AI algorithm, meaning that it does not generate any explanations. Starting from training to output, the model takes some training images. In this case, we have two classes, the benign and the malignant class. Once we input it, because it's evolution from a pre-trained on, and in this case to use net with specific different if you want layer, putting the image features from these images, base feature to a fully connected. The neural networks to apply these training images and to the output logic. For example, identify 9 with 97%. And based on the algorithm goes through correct winning of the neural learn more and better. If we can.
we will be you will be comparing the network. Black, then we always don't open the.
If we can go to the next slide. Okay, so after training, we go to of the model, so to images from the test set. The test image goes through the trained model, and we get a classification whether it's hold matrix. In this case, we achieved a 9 almost a bit more exercise, and we will see how we get this result. Next slide, Doctor. Okay, so we thought the black box, but how to make it explainable? We took the same convolutional neural algorithm and added the prototype layer. So during training, the prototype layer extracts important images. We call these parts, and they represent the features that these convolutional layers are learning. Evidently, the model is learning. So the model learns a similarity metric between these. And based on a similarity score, we pick a class based on the weighted sum of the similarities between the prototypes. So some of these prototypes, the nearest patch and similar prototypes, they come from differences. So these often correspond to types. And thus we prune them, so we omit those prototypes from the model. And finally, once the training for interpretation or to generate explanation, once we input a test image, the model tries to find evidence the test image belongs to a specific class, bases it to all the prototype it has learned, and marks the activated patches in the boxes. So these are very similar to what prototypes this model has learned. The heat maps show us which part of this image is similar to a prototype.